so let's continue looking at the eye. So now we're going to look at that next layer of the eye, which is the sensory tunic, shown here in yellow. All right. Now what that is that's the retina. So this is the inner layer of the eye wall that contains the photoreceptors. So the receptor is sensitive to light. All right. It is continuous with the optic nerve, so you can see that their retina just becomes the optic nerve there. Now let's look at a couple of structures that we find on the retina. So one is a macula lutea. So right there, macula means spot, lutea means yellow, yellow spot. So this is a yellow spot in the central region of the retina. Now in the macula lutea is a small depression known as a fovea centralis. So this is a depression in the center of the macula lutea. So fovea actually means a little depression, all right? In actuality, the fovea centralis is where we get our sharpest vision. So when light rays hit our fovea centralis, that's where we're getting our best vision. Next is the optic disc, which you can see over there. So the optic disc is an area where the nerve fibers leave the retina and they join the optic nerve. So if I go back to this previous picture, in this area here, here's the optic nerve, so this would be the optic disc. And because our retina is kind of made backwards, this leads to these nerve fibers going in this direction, and because of that, we actually lack photoreceptors there in the optic disc area, and so this creates a blind spot there. So it lacks these photoreceptors altogether. Now, you don't notice that blind spot because the peripheral vision of your other eye can see in that area. All right, let's take a look at chambers in the eye. So the first, the one I'm going to talk about is the posterior chamber. So the lens is essentially the divider on these chambers. So the posterior cavity is the cavity behind the lens. And it contains what is known as vitreous humor. So there's a clear gel of the posterior cavity. It transmits light. It supports the posterior surface of the lens, holds the lens in place, and it holds the retina against the choroid, pushes the retina there. And the front part of the eye is the anterior cavity. So this is the cavity before the lens. So as I said, the lens is the divider. Now with that anterior cavity, we have we have a divider here. We have the posterior chamber, which is between the lens and the iris, and we have the anterior chamber, which is between the iris and the cornea. All right. Now the fluid in here is called aqueous humor. So aqueous humor is a clear fluid in the anterior cavity, and that fluid is what is made by the ciliary processes of the ciliary body. So it is filtered from plasma, so it provides nutrients and oxygen to the lens and also to the cornea. And it exits by these small little holes here, which are known as canals of Schlemm. So what happens with somebody with glaucoma is that pieces of the vitreous humor get into the anterior cavity and they block those canals of Schlemm, which creates a lot of pressure here in the front of the eye because you constantly are making that aqueous humor. And the long-term consequence of this is blindness because that pressure can push against the lens, which pushes against the vitreous humor, which pushes against the retina, and that pressure would kill those photoreceptors. All right. Let's look at the physiology of vision. So this is all based upon refraction. So refraction is a bending of light through a medium. So lenses are going to bend light rays, all right? So a convex lens, like this lens here, our lens, what that does is it bends light rays to a point, which is known as a focal point. A concave lens, which is what you see here, so a convex lens is thicker in the middle, thinner on the edges. A concave lens is thinner in the middle, thicker on the edges. A concave lens is going to bend the light rays out. They're going to diverge, all right? So our lens, as I mentioned there, is a convex lens. So we're going to bend those light rays to a point there, and that point just occurs right before our retina, all right? Now the image that forms there is upside down and it's backwards. So they're showing the arrow this way, here it is upside down there. All right? So in normal vision, the focal point hits in the right place. So if I go back to here, here is the focal point, and then that image that forms on a retina forms in the right location. All right. If somebody is nearsighted, so this is trying to show myopia or nearsighted, that image forms too soon. All right. So here the eye is too long for the lens that it has. All right. And so what we do in somebody who is nearsighted, what happens here is their lens flattens for close vision. So when they're looking at something close up, their lens flattens out so they can see that. But that's not the proper thing. Our lens is supposed to flatten for distant vision. It's supposed to thicken for close vision. But it's flattening out for close vision, and so it can't flatten out anymore for distant vision. All right? And this is corrected with concave lenses. So those lenses cause the light rays to diverge further out before they get into the eye, and so the image forms in the right location. All right? So if you are nearsighted and you wear corrective lenses for that, what you might notice about those lenses is they are thicker on the edges, thinner in the middle. In fact, if you wear contacts, contacts work by the same physics. Those contacts are going to be thicker on the edges, thinner in the middle. Next is hyperopia. So this is showing a hyperopic eye. Here, the focal point comes too late, and so the image would form behind the retina. In either case, the image forms too late, or gives a distorted image. So with this here, the eye is too short for the lens that you have. All right? And so what happens with these people, how they're able to see far away and not close, is that the lens thickens for distant vision. Now, once again, this is not what's supposed to happen. Your lens is supposed to thicken for close vision. So since it's already thickening for distant vision, it can't thicken anymore for that close vision. All right? This is corrected with a convex lens, so that gets the light rays to come in earlier so that the image forms in the correct location of the eye. Someone who has astigmatism is where you have an unequal curvature in either the lens or the cornea. And so by having an unequal curvature, it leads to light not focusing on one point, and you get a distorted image. All right, let's take a look at those photoreceptors. So this is a blow-up of the photoreceptors. This is a rod, this is a cone, and they are named for their shapes. All right, so if we go here, this is showing the different layers of the retina. Here's a rod and cone layer, bipolar layer, and then the ganglionic layer. So we have rods, cones here. Okay, now rods are photoreceptors that detect dim light and peripheral vision. They're more numerous, so we have a lot more of those in our eyes, and they are more sensitive to light. They have a lower threshold potential. So, so if it's dark outside, you're primarily using your rods in that situation, those low light settings. The thing about that is they don't provide sharp images, nor do they provide color vision. Next are cones. So right here are cones. So cones are photoreceptors that operate in bright light and provide color vision. They also give us the sharper vision. All right? And we have three types for detecting different colors. We have red, green, and blue. Okay? And those allow us to see all the colors of the visible spectrum. All right? So if we go to this next picture here, this is showing the blue, there's a green, and there's two different forms of red. And then these are the colors when they get interacted with and how much they're activated. We interpret those different wavelengths of light as different colors. So we have three different cones. These guys, manna shrimps, are kind of awesome here. They have 12 cones here. So pretty awesome, huh? The thing is, we actually see colors better than they do, different shades of colors, and that's because we have such a large brain. They got little brains, so they can see this color well, and that color well, and that color well, but they have trouble with shades in between, okay? So unfortunate thing about them. Now, some of us will have color blindness. This is a congenital lack of one or more cone types. The most common is red-green color blindness. It's a sex-linked trait, so it's much more common in males. Right? So when you look at here, I'm hoping you all can see the 28 and the 16 that's found here. So 28 and 16, I'm totally joking. It's 74 and 5. Okay? Some people can also have night blindness, and this is where your rod functioning is low, and that's usually due to a vitamin A deficiency. All right, let's take a look at the visual pathway. So we're going to go from the optic nerve into what is known as the optic chiasma, and that's where these nerve fibers are going to cross over. So the lateral portion crosses over there, and it goes to the primary visual cortex of the occipital lobe. And so by having this crossing over that occurs, some stay on the same side, some cross over. When we get over here, what we do is we fuse these slightly different images together, so from the different eyes. All right, so we have one cohesive thing that we're seeing. Also, because we have this area where our visual fields overlap, that gives us binocular vision in that area, and that allows us to have depth perception. So we know how far away something is. Okay? So some of these tracks are going to go to the superior colliculi, and then we get that reflex for moving the eye there.